Alright, so in this new playlist, I'm gonna be talking about several papers, each video one paper, and I will go through equivariant neural network, equivariance in graph neural network, different kinds of equivariance like steerable CNN, steerable convolutional neural networks, and many things that are related to geometric deep learning. But the first video, I want to emphasize on application of that to the natural language process because it is often overlooked. People only focus on computer vision applications, and mostly, of course, but it has many applications. It has applications in natural language, like dependency parsing in this article, that I'm going to be explaining in this video. Dependency parsing with structure preserving embeddings. For example, when we have a tree in dependency parsing, this one geometrically is very similar to this one. Because, when you go to breadth first search, BFS, at the third level, you see that this one now is shifted to this one. So this is another. So that's why I like Professor Christopher Manning in Stanford. He's always ahead of time, and he always knows what will happen in future. Many years ago, he knew that these things will come in future. People will talk about geometric deep learning, and they will see that there are applications in natural language as well, in graphs, in speech, computer vision, everywhere. So let's focus on this paper only in this video. Modern neural net approaches to dependency parsing are trained to predict a tree structure by learning contextual representation for tokens in a sentence, as well as a head-dependent scoring function. Whereas this strategy results in high performance, it is difficult to interpret these representations in relation to geometry of the underlying tree structure. Because if you just care about head dependent, and we don't care about their geometry inside, for example, a tree, then we are not efficiently using there is a branch of deep learning, we call it efficient deep learning. It means that we want to use neurons very efficiently so that we don't need to have millions of neurons. With very few neurons, we can do lots of things that are equivariant to translation, rotation, different group transformations, and we can efficiently use symmetry. The reason that you see symmetry, this flower, symmetry in nature, many things in nature, many fruits, many vegetables, flowers, everything in nature, even human body, the reason that it's symmetric is just because nature wants to encode information efficiently, so that there is little need to store information. Because if it is small, if encoding is small, then you can efficiently store it with little amount of storage, and that's why you see symmetry in nature everywhere. So our work seeks instead to learn interpretable representations by training parser to explicitly preserve structural properties of a tree. We do so by casting dependency parsing as a tree embedding problem, where we incorporate geometric properties of dependency trees in the form of training losses within a graph-based parser. We provide a thorough evaluation of these geometric losses, showing that the majority of them yield strong tree distance. I have a playlist about metric embedding that for example, I talked about tree distances how we have, when we have a graph, how can we, for example, how can we embed each node so that it preserves the distance. And so you can watch that playlist for metric embedding. And so you see, why don't we use symmetry? We should use it everywhere, because if we use the symmetry, then we can have efficient deep neural networks. For example, this transformer architecture is a complete graph. We are not using any type of symmetry in transformer architecture. For example, this hype of LLM, everybody in all the universities of the world are working and pushing everybody to work on these things. So I think it has become a little bit hype and pseudoscience, because there are many things that we can improve current deep learning methods, like symmetry and duality. Duality is another topic. Symmetry is about geometric deep learning. So why don't we use that? Otherwise, it's just all the papers that you see is just repetition of what they do, and we don't see any new innovation. But the great people in Amsterdam University, they are working very beautifully on this topic, and we should thank them for innovation, because they have shown the world that we can have a more efficient deep learning if we just change our mind and just free ourselves from just the hypes and what everyone else does. If we focus on nature, then we will see that symmetry is everywhere. That's why we have many different versions of equivariant neural networks, thousands of papers about equivariant neural networks. So let's focus on this one. So we want to care about this is a dependency parsing tree, very beautiful, but we are not caring about the metric embedding on this tree. We only care about, okay, this is head and dependent, and just sometimes overfitting in order to just achieve the task. But there is more to that. We can have efficient representation of this feature. So, for example, if it is invariant to some kind of group transformations on the tree that you can define. So here, this is the Pythagorean embedding, very important. Given a rooted tree where R denotes the root, then there exists an embedding, this embedding into Rm, such that their distance, the tree distance, for any UNV that you imagine, their tree distance is equal to Euclidean distance. And moreover, you can write f of any node, phi of v, to the phi of root plus a zb, where z is just orthonormal columns. So using this, we can rewrite the L1 distance as well, like this. But the corollary is interesting, that given an isomorphism, then the embedding G of V is an isometric embedding of same tree into our cardinality of E. So we are trying to use these geometric losses that we want the tree distance between 2 points, 2 nodes on the tree, to be similar to their equivalent embedding on their embeddings. Because phi is just embedding into Rm, so this one is just on Rm. The distance is on Rm, but here is on a tree. We want to make them very similar. Of course, when we predict them, we see that still it's not perfect. We have some error, but still we are trying to do that. In convolutional neural networks, in equivariant convolutional neural network, the trick that they use, they just represented in the structure of the convolution, because convolution is just translationally equivariant, but not rotationally or scale or other kinds of transformation. So they think they inherently put it in. But here in this paper, they have another trick for equivariance. They have another trick to make use of the symmetry and the metric embedding. They just explicitly put it on the loss. There are very few papers do something. Of course, many papers that are about metric learning, they have the same paradigm, but they don't do it just because of geometric embedding and geometric concerns. So this is when we do it, when we say that you see, this is a head, this is dependent, then this is head for the next dependent. Each dependent has only one head, but each head has it can have many dependents. So what we want is that this distance is always 1. When we go from, for example, in breadth first search, you have different levels. From one level to this distance is always 1. The same thing when you go to the delta ij is also 1. So this means that, from the root, so this means that we are preserving the distance. We put it explicitly in the loss. You see, this is the softmax of the loss, and softmax that we have created to predict the embedding. Of course, tau is just the hyperparameter for temperature. And then we have a natural loss on both the embedding. And then we use cross-entropy loss here. But the rest of that is just classic, because this is just one way of doing dependency parsing. We have a head module, we have a dependent module, and then we concatenate them, or even use this bi-affine function, and then we predict. This is the idea of Professor Christopher Manning in Stanford. That is very beautiful, and thousands of people have used his idea because it is beautiful. And so that's it. So we should always use these group transformations. In the next videos, I will talk about group transformations, different kinds of groups. You don't need to have a big background in group theory to know what, but at least you should know for example, what is a stabilizer of a group. For example, you should always try to think about these things. For example, yesterday I bought this Rubik puzzle for my niece. So you see, when I play with this, I see that every time we have a new kind of symmetry. So symmetry is everywhere. You can put it in your graph neural network. You can enforce it on your any design of new kinds of neural networks, such as graph neural network. But unfortunately, most of the literature is about CNN. For example, we have many equivariant neural network for CNN, but maybe 80% of articles are about CNN, 10% is about graph neural network. Of course, they're also related to that 1WL test and many versions of that. So sometimes geometry helps topology as well, because the next generation so that's why topological graph neural network, whatever we do, it has some benefits for geometric neural network as well, geometric graph neural network as well. And there are some fields in pure mathematics that we have, for example, geometric topology or topological geometry. It means that sometimes geometry helps topology, sometimes topology helps geometry, sometimes geometry helps topology. But if you use the symmetry in nature, if you use symmetry in deep neural network, we can have efficient deep learning. That's it.